So we're going to go ahead and go live. My name is Rachel Burson, and I'm welcome you to this session of RoboLaunch, where we're going to explore robotics and invite students from around the world to learn about some of these opportunities. I'd like to invite Kylie Barber, one of the Robotics Institute Summer Scholars, to kick off the session. Kylie?
Hi, everyone. My name is Kylie Barber. I study mechanical engineering and mechatronics at Penn State University. This summer, as part of the Robotics Institute for Summer Scholars, I'll be studying compliant origami mechanisms within soft robotics swimming context. I have approximately 50 of my fellow scholars here in the room with me today, and I'll be helping to facilitate questions along with my colleague Larry, and we'll get questions from the room so that we can all participate as well. On behalf of the RISC 2022 class, I want to say welcome to this RoboLaunch session. It is my honor to introduce Dr. Maja Matarić from USC. She is a professor who studies neuroscience, computer science, and pediatrics at USC Viterbi. Dr. Matarić earned her master's and PhD from MIT in computer science. She focuses on the field of socially assistive robotics, which tries to understand the interaction between humans and robots, and also creates robots to help facilitate that interaction as well. Her work is multidisciplinary, encompassing neuroscience, cognitive science, social sciences, health sciences, and education. Thank you all for being here today, and we look forward to your talk.
Thank you. I will go ahead and share my screen now. If you let me, let's see. Here we go. All right, and you'll have to tell me if everybody sees, oh, sorry, actually, one more sec. I forgot to share with audio because I'm going to have videos with audio. Okay, here we go. All right, and then you just tell me if you actually can see the screen properly. Yep, can you folks see it? I can't see you, so you'll have to tell me through audio if you see it. Okay, yes, great. When we go back, or if you can still see me, you can see my background. The background is basically a collage that my undergraduate students put together for my birthday. They do this every year to some song that I like by my favorite band, which I won't give away. You'll have to look at the background and figure it out. But anyway, this is all to say that the reason that I do what I do is because of the amazing students that I've had the privilege to work with for decades now. So what I'm going to tell you about is, I think, quite exciting. It's a new and growing field, but the original idea to start to get into it, what came from a student, the name came from a student, and all the great work that I'm going to talk about is really done by students. So that's really to empower you to realize that, you know, you're the ones that make these things happen. So please do. Okay, so I'm going to tell you about the future of personalized socially assistive robot companions, because that's what I work on with my students. So as you know, robots do work, right? That's what the word robot means. Robota means menial labor in Czech. But actually these days, if we look at what robots are doing or being created to do, it's really everything that we can think of. So people are just coming up with ideas and thinking, gee, can we make a robot do this? I don't know, let's try. And as we're doing that, I would like people to think a little bit harder about the implications of that. And so we start with students, because students, again, are the ones that are doing the work and shaping the world. And it's the world you're inheriting. So let's think a little bit about what that world is going to look like. So I would like to challenge you to think about, if you're doing robotics, or even if you're doing AI more generally, what are you doing? And why are you doing it? And what's it going to do to the world? Ooh, does that seem a little heavy? Well, I'm glad, because you really folks are shaping the world. So what are you creating? So right now, if you think about what we're doing with robotics and AI, it's mostly automation. The idea of automation is the idea of replacement. So it used to be in robotics that we used to do dirty, dull, and dangerous things with robots, right? We create machines to take work away that people don't want or shouldn't have to do. But that's really not what we're now. We're largely looking at automating most things. What we're neglecting, by and large, is augmentation, namely enhancing human ability to do whatever it is that we as humans would like to do, so that we become more empowered and still have a role. And so what I want to tell you about is this field that allows robots to be very useful and even lucrative, because everybody now wants to make money on AI and robotics. So you can do that, but not necessarily by doing automation. So not necessarily by replacing human work, but instead by augmenting or enhancing what people can do. And I think that's very important. So I would urge you to think, don't just do something because you can, and don't just take a job because it pays well. Think about what it does to the world. All right, so with that, let's talk about this field of socially assistive robotics. My lab started this field and named it back in, 2005. We had a paper that named the field. And then, of course, many people are doing work in it now, and it's a wonderful, thriving field. But I have this fortune of having named it by a graduate student of mine, David Feilseifer. And, now it's a field, and you can get grants for it from NIH and NSF, and you can publish paper in it. And there are even startups in this space, and it's very exciting. So that's the kind of wonderful thing one can do from research. And there was a wonderful article in the New Yorker about it in 2009. So it's kind of fun to see how the field has evolved since then. Some problems are solved and others are far from being solved. But this idea of socially assistive robotics is really the idea that robots are there to support people while they do their own work and help themselves, rather than doing the work for them. And they're doing this through social rather than physical interactions. And we'll talk about why that's important and why it's better to do this not with apps. So we already know in this world of the quantified self that you can have an activity band that tells you how many steps you've taken and your heart rate and heart rate variability, et cetera. And, it can tell you how much you're sleeping. Unfortunately, all those data are not really changing your behavior. If that were the case, we would have a lot less heart disease and diabetes and, opiate addiction and everything else. But behavior change is hard. So just having the data about your behavior and about your state is really nothing in the problem of changing behavior. What does work is coaching and training. And there are apps that will do coaching and training, but they're also largely ineffective. Why? Because behavior change is hard, and we need motivation in order to really push through the hard stuff. And it's mostly hard stuff. If you have any kind of a challenge that requires therapy, a change in lifestyle, a change in behavior, that's extremely hard. If you're recovering, or if you're just, whether it was an accident or whether it's a long-term issue, how do you get the motivation to keep pushing through? And that comes from social support. And so the idea is that where there aren't people to provide that social support, you want intelligent embodied agents. Why do they have to be embodied? Why do they have to be robots? Well, we'll talk about this. Some of them don't have to be robots, but it turns out if they are robots, if they're physically embodied, they're much more effective at motivating you. Why? Because you're a human and you're wired to respond differently and more to physical creatures around you than to screens. So this is really exciting because it's a convergence of technologies and disciplines, and it's constantly moving. As you'll see, there's so many branches of it. But if we look at the history over the last 17 plus years of this field, back when we started, and these are examples from my lab, obviously, but they're examples from other labs as well. So in the early 2000s, when the field started, we looked at some real world areas, and that's really how the field began, was getting out of the lab. I would say the most important thing in doing some truly meaningful work is to get out of the lab. One day outside of the lab is worth a year in a lab. So think about the value of your time. Anytime you're outside of the lab, learning something about the real world, collecting data in the real world, you are doing something more meaningful. So get out of the lab. Okay, so we started out as a field with these short-term deployments, one day at the cardiac clinic, one day in a rehab clinic, one day at Children's Hospital with kids getting pain treatments. And then we went, after about a decade of that work, we went and started doing longer deployments, like stay at a school for 3 weeks and interact with kids, twice a week. So 6 sessions, or going to a retirement home for a month and interact every other day. And now, in the last few years, the field has gotten to where a few brave souls, including our lab, obviously, because we feel the burden having started it, have actually done things like developed robots and left them in the homes of families with children with autism for over a month at a time. We have left robots in nursing homes for 6 months at a time. So that's a level of autonomy and a level of complexity that's really, pushing the boundaries of current state of the art, not just in robotics, but also in AI, machine learning, dialogue, NLP, NLU, all of that stuff. So it's very exciting because we can start to look at some real problems. And that's what I want to tell you about, real world problems and what these systems can do for those. So what do we want to do? Well, we want to help people, empower people towards behavior change, to help people help themselves. How? Well, how do you get people to generate and sustain motivation and stick with something that's really hard to do? Computationally, that means that we're going to model some phenomenon like, let's say, grit or motivation or personality or engagement. You'll see the examples. And then we're going to model the user, again, computationally, but by collecting data about the user, because we have to personalize to that user. So we have to do some interesting machine learning that will personalize the interaction for each individual user, because there are no generic answers. This is not where generic big data will help you. This is not a standard machine learning problem. In fact, it's everything, it's anything but. So we'll get to that. All right, so now a little whirlwind about robotics in this world, right? Robotics is hard. It's hard because of uncertainty. You're in the physical world and nothing is certain. The robot doesn't know exactly where it is, exactly where it's sensing, where is the human, what is the human exactly doing? These are not problems that will be solved really anytime, because the human brain also doesn't know for sure, but does a wonderful job of compensating. So with all of that, then you have to worry about social things like, what is this robot, the robot is trying to do? What is this human wanting to do? What are they going to do? What do they want? What do they desire? Are they happy? Are they achieving their goal? Am I too close? There's a lot to worry about in the social space. So let me give you a few examples. Here's an example of beautiful work of a PhD student of mine, Lauren Klein, who's graduating a year from now, where a robot is absolutely necessary. She is using a robot to get babies to imitate certain behaviors so that they can heal and learn to move if they have early movement delays. So let's see what that looks like, and then I'll explain. So there's a baby. They are so cute. And there's a robot, and the robot is showing the baby what to do, which is exciting because if an adult shows the baby doesn't imitate because adults are too big and the mirror neurons are not triggered, except for faces. But when the robot kicks the ball, the baby learns to imitate. And this is how, by the robot doing specific behaviors, we can get the baby to do specific behaviors that the baby needs to practice if the baby is at risk for example, autism. Now, this is exciting if you think about it, because how else are you going to get a baby to do something? You tell me. You can't make babies do anything. Babies do what they want to do, and they don't do a lot. So how do you do it? So it turns out the robot is a fundamentally necessary way to do it. And if you try to do it with the screen, it doesn't work. So you could show the baby the video of that robot and the baby doesn't imitate. So it's an amazing example of where the robot embodiment is necessary to do something. But sometimes the robot's body in the real world doesn't have all the affordances and features that you would want. So another area that our lab is exploring, and it's the work of Tom Greschel, another senior grad student with wonderful talents. And Tom is one of the leaders in the field of mixed reality and robotics. So the intersection of mixed reality, such as AR and VR, and robotics. And yes, some people want to talk about it as the metaverse, and you're going to hear that buzzword a lot. But fundamentally, what's happening is we're creating another shared world between the robot and the human. There's the physical world, but that world is hard for the robots to really understand and manipulate. And then the person doesn't know much about the robot. So now we can create this shared augmented world where the user can, for example, see what the robot is sensing and maybe even see what the robot is thinking. And so this is really exciting. We're using it to, for example, teach high schoolers to code by moving their bodies around and playing with the robot in the physical space. And that's important because one, coding is important in 2020 plus, and two, moving your body is the best way to learn. So this idea that we should all be sitting down in front of screens, it's actually a terrible way to learn. You learn much more, you retain things better, you recall them better, and you're happier when you're actually moving around while you're experiencing things. So that's Tom's dissertation, is creating this shared world between the robot and the user where there's a lot of movement and therefore a lot of enjoyable learning. All right, but when you have a body, then embodiment inspires bias. So for example, one of my other students, Nathan Denler, with the help of a new student, Nina, did a study on gender perception in robots. And just in a quick nutshell, we took a robot that's sort of gender neutral, And I say sort of because every robot that you look at, you in your mind aspire some gender to. On a continuum, of course, not necessarily binary, but you aspire it, you assign it, you can't help it just because that's how you're wired. You may not consciously think about it, but if I force you to tell me what gender is that robot, you'll have an answer. So that means somewhere in your mind, you've already created a bias. And we're very, very biased, right? So it turns out in a study that Nathan ran, if we gave the robot a voice that was distinctly sounding more male or sounding more female, that drove people to believe that it was one gender versus some other gender based on just the voice and not appearance. But if the voice is neutral, androgynous, then how the robot is dressed obviously is a bias, but the profession biases it even more. So if it's a medical worker, people assume that it's a doctor. If it's female, they think it's a nurse. So again, there are all these cultural biases that we have deeply built in. And this study was done both on Mechanical Turk and with college students. And you'd like to think that you, college students, are not biased. But I hate to tell you, you are. So check your biases when you're creating robots, because even when you're creating a robot and programming a robot, your biases are coming through. Now, that was just about the body. Now we get into interaction, which is the really interesting stuff, right? All the little complex things, taking turns, understanding others, understanding social roles. It's really the fun stuff. This is why we do what we do. Recently, a student of mine, Lena Mather, who's coming into the PhD program at CMU, as it happens, she was an outstanding student, but I'm going to keep collaborating with her, so I can't let her go fully. Anyway, Lena did a really interesting study on trying to develop an automated lie detector because, you know, people are terrible at lying. The best you can do, you think you're really good at it. Everyone thinks they're good at it. Everyone's terrible at it. So we're about 50%. We're actually at chance at detecting whether someone is lying or not. That's because actually we have this inherent bias to believe what people are saying. It's hard to believe that when you hear it. You think, no, I'm discerning. But in fact, no, you're not. You are on average at chance. Now, computers are much better. So AI, machine learning based on training faces is much better. And what Lena did was to go well beyond that and use multiple features. So she used the emotion in the face, visual, verbal, and vocal cues, and was able to detect lying with really high accuracy, you know, in the high 80s. Much, much better than any human can, even the highly trained humans. And then she was also able to do this in an unsupervised way. Now, it was a little tricky because there were implications to this work that maybe she wasn't the happiest about. But the main reason why we did it was we wanted to get to a point of detecting when people are not telling the truth, because we're interested in therapy robots. And we want to know, for example, if we're asking someone if they're having suicidal thoughts, we want to know if they're lying to us when they say no. But you have to think about the implications of your work. We might be thinking about preventing suicide, but somebody else might take this work and do something really different and undesirable with it. So, you know, think about it. Think about your work. Another direction that we have worked in is modeling empathy. So people have thought about how to create robots that look empathetic, right? And behave empathetically. Like they can say to you, oh, I'm sorry you're stressed, or how can I help? But what we're interested in doing is something harder, which is we want the robot to do something that will make the person be empathetic. Because in general, when people are feeling empathy and behaving empathetically, it's better for everyone and people actually feel better. So we did this interesting study with a collaborator, with Lena and also a collaborator in Italy, where we, during the pandemic, we conducted it in Italy, completely at a distance. It was very interesting. And we did this interesting storytelling story to figure out when people were feeling empathy, and then, you know, to see how to make people feel more empathy in interactions with the robot. And there's a journal paper about that. But anyway, exciting stuff about understanding human empathy. And this is important because it turns out that people are actually quite mean to robots, or can be. People kick robots, they hurt robots. Why is that? Why can robots bring out the worst in us or the best in us? We want to create robots that bring out the best. And here's an example of that. In another line of work by my student, Chris Birmingham, we're creating robots that will help people in therapy support groups. Why? Why wouldn't humans do this? Well, humans experience burnout. Human moderators of support groups experience burnout, and there's a huge need. And so throwing in an autonomous agent, which is not judgmental and doesn't keep any private data could be a very effective way to scale up support groups. And this is building on some prior work of my former student, Elaine Short, who's now a professor, where she created basically a robot that would moderate group discussions. And the robot, which couldn't even understand what people are saying, but could just see who was talking and how much, was able to get the group to be much more friendly and less selfish. So this was really exciting work, and now we're building on it for the therapy context. And then finally, very briefly, machine learning, hardest thing, right? But there's no such thing as a monolithic machine learning approach. You need machine learning at every level, because the robot can't know everything it needs to know, because the world is uncertain, and because the user keeps changing. Users are always changing. Within a session, they're curious at first, then they get tired. They're learning things, so they get better over time. And then also, if they're elderly, well, they're getting older. If they're younger, well, they're getting older also. So there's always change over time. So many things to learn. In one example of our ongoing work, Lauren Klein, the same amazing student working with babies, still working with babies. Now she's looking at detecting infant and caregiver toxic stress, because in interactions between caregivers and infants, when the caregiver is experiencing stress and not necessarily looking at the baby as much as is typical, that causes developmental delays in babies. Well, I can tell you all the mask wearing is also going to have interesting developmental effects on babies from the last 2 years, but that's a whole other thing, because what can we do? We have to do it. But there are a lot of critical things that happen in early development in terms of what babies see in other people's faces that are critical. And so we're interested in modeling that and then helping caregivers to realize that things are atypical and get help. And then I want to just show you the video of a kind of an amazing tour de force work, which probably involved about 50 different undergraduates to develop and then deploy this robot in homes of kids with autism. This is a little bit of a video. This is Science Nation, so you can find it on the web. I just want to pique your curiosity, then you can easily find it.
Meet Adrian, age 6.
This is some great work.
And his robot friend, Kiwi.
You are doing an amazing job.
On this weekend morning, they've settled in to play some games, along with big brother Darren. Adrian is on the autism spectrum, and Kiwi is no toy. It's a socially assistive robot.
You are doing really great. Keep up the good work.
Okay, so without going into details, you should all look up this video. It's beautiful. It was done by the National Science Foundation, and it shows our wonderful undergraduates and some high school students who were involved in this project. But the really fundamental thing is anyone can have a screen and try to learn from a screen, but it's not very effective. It's very distracting. Sure, it's fun to play games on a screen, but if you're actually learning, let's say, math, and then you hit a snag, well, intelligent tutoring systems can kind of give you a little bit of support, but you don't get any social support. You don't really feel better. And so the idea of this robot is that it's both a social support mechanism for the child, but it's also teaching them social skills. So the robot can, for example, say, oh, how about if you try another one? And then the boy can answer something. And if he doesn't look at the robot in the eye, the robot will say, oh, but I like it when you look at me, because then it makes me feel like you're paying attention. And so basically what's happening is what should happen in preschools and schools. And during the pandemic, it could not, which is that you're helping children develop their social and cognitive and emotional skills all at once. And that's what happens in the real world. But it is very hard for that to happen for children on the spectrum, because other kids won't play with them. And then during the pandemic, there was a reduction of social play and interaction anyhow. And so, we can have these kinds of companion agents to bridge the gap. So I just want to show you this last video. This is a 3-year-old with special needs interacting with a robot in real time. There's no person behind the curtain, real-time interaction. Why didn't we all have this during the pandemic when my students developed this like 5 years ago?
From 1 to 6. Count them out loud with me.
So the child has to do the right thing, say the right thing, look at the robot.
2.
And then the robot will give feedback verbally and physically and advance the game. And if anything goes wrong, then you cannot proceed until all the right things are done by the child. So this beautiful real-time interaction, physical and verbal and in the game. And that's a tutor. So that's what we need. But who is working on that? Most people aren't, because it's hard, because you have to get real data in a real environment. This is an actual preschool in a low-income area in LA, where my students worked for 3 months to get data. And that's fantastic. And we learned more than, other people did from data sets they downloaded off the web. So bottom line, well-designed systems for human-machine interaction, not even just human-robot interaction, but human-machine interaction in general, can be very empowering. And there are a lot of results now to show improved health outcomes and learning social skills, learning emotional regulation, improved learning in general. But this only happens if you work on real-world problems and in real-world contexts, not just the lab, and on real-world data that you get from the real world. So I really want to motivate you, since you're students and you're looking at this big, bright future ahead of you, work on meaningful things. Please do. Use your wonderful, amazing brains to do something useful. And with that, I say thank you to my amazing students, and I'm ready for questions. And thanks for having me.
Hi, thank you so much for your talk. I found that really interesting, and I'm sure a lot of us did as well. We have Larry here, who's also going to help me facilitate questions. If you'd like to introduce yourself.
Yeah, hi, thank you. Thank you, Dr. Matarić. So I'm Larry. I'm actually a rising senior also at USC, so fight on. Yeah, and basically what we're gonna, I'm majoring electrical engineering and applied math, and I'm here with Dr. John Dolan, working on human vehicle control, human vehicle manipulation through autonomous vehicle. And basically what we're gonna do is we're gonna alternate between the live sessions from the webinar, from the live web, and also the classroom full of first students in front of me. So why don't we start with Kaylee? I think you have a question, right?
Hello, thank you for your talk. My name's Kaylee Barber. I had a question for you. I was looking at the robots and you had a bunch of different designs, like none of them really looked the same. And I was wondering how you chose like the physical design of the robot and how you, I guess, like interviewed kids, or like how you figured out what it should look like for kids to want to like work with it.
That's a great question. So what should the robot look like? So we're sort of really limited in robotics research today because we can either buy one of the existing platforms, and they're very few, and they're really not built for human robot interaction. They're built for other things like manipulation, navigation, things like that. Or we can design our own. And when you design your own, which we've been forced to do, you kind of can't do it all the time, right? You can't do it for every study. So we tend to design a robot every few years. We're doing a new one right now that's going to be a soft robot, very exciting. But so we do exactly what you suggested. We talk to members of the user communities that we're interested in. So when we, for example, designed that owl robot that you saw that was used in autism, but it was also used with the elderly. We talked with elderly users, and we talked to parents of kids with autism, and we talked to kids with autism. And we learned some really important things, like everybody liked the owl because it implied something about being smart. So people like that. It's like, oh, okay, that's good. Doesn't have to be human, but because a humanoid robot is very expensive and dangerous, right? So we don't do humanoids. I'm not really a big fan of the Now robot because it's so small. It doesn't have an expressive face. So we've used it, but we only use it with babies because with babies, it's the right size. It's the size of the baby. And you can't ask a baby what they like. That's a trick. But when we talk about, for example, the elderly, we talk to them and they like the owl because they said, oh, it looks smart. It will know how to help me. But then when we tested the owl with kids with autism, we actually found out that they would many of them would pull on the wings. So we took the wings off. Why is that? Well, they might really enjoy pulling on the wings, but we're trying to create a social partner. So you don't want to let a user get used to doing something with the robot that they cannot do with other people. Because the whole point is that we're teaching kids social skills. So you wouldn't come up to another person and start pulling their hair or their arm. So that is to say that when we design these robots, we really talk to the users, we look and we test a lot. We don't just say, oh, okay, we have enough information. Here's the robot. Let's run the study. Because if you do that, then you'll find out all kinds of things like, oh, well, they keep pulling on the wing instead of paying attention to what the robot is saying. So it takes a lot of trial and error, iterative design. But if you think that's interesting, I think it is. If you think that's interesting, there's a whole new field of robot design that's just starting to emerge. And it's the intersection of basically design, and design thinking, and problem solving, and then robotics and human robot interaction. So this is a new area that's just starting to emerge, and it's really interesting, and it's going to be really creative. So yeah, look into it.
Okay. Thank you so much.
Thanks.
We have another question from the room as well, from Raina. If you'd like to come up and ask your question.
Hi, I'm Raina. Thank you so much for the talk. I had a question with regards to social robots trying to read emotions and also portray emotions. So for example, in daycare setting or in therapy settings, what are some of the data points you take in? How effective are those data points in detecting the actual emotion? And furthermore, is there work being done for robots to portray those kind of emotions?
Great questions. Let me make a correction to your question to begin with. These are not social robots. These are socially assistive robots. There's a really big difference. A social robot can be a really fun, entertaining machine that, distracts you, makes you smile. You can use it to measure human behavior. That's not what we're doing. We're creating socially assistive robots. The assistive part is important. It means that it measurably changes your behavior. It's assisting you in doing something. And I really draw that distinction because there are a whole bunch of social robots. People are creating all kinds of things that are cute and entertaining, and they want you to spend money on it. That is not my goal. The point is that there is a measurable behavior change. So that's why I really want people to understand the difference. Socially assistive robotics have a purpose. There's a purpose that they're trying to achieve. Okay, now that purpose could be, as you were saying, relating to, for example, understanding the emotion that the human is expressing so as to help them, let's say, for example, I want to teach a child to express empathy, which is a tricky thing, right? So how can I measure whether the child is expressing sorrow when I, as a robot, am telling a sad story, which is exactly what we did in our study, right? So the robot is telling a sad story, and it's behaving in a way that appears sad. And we want to see that the child is actually expressing empathy, in a sense, mirroring that sadness. So indeed, we take a bunch of data. We look at body pose, we look at facial expressions. It's not enough to just look at facial expressions. There's an entire field in human-computer interaction called affective computing, which means computing related to emotion. But it's affective computing from images and video is very, very different from affective computing with real robots in the real world. And so it's still, it's not like doing things with real robots in the real world is always harder. But yes, we take all the insights from all of the fields, and what we're looking at is developing models for each child, because just because you might have some general model that says, this is a smile, well, it turns out the smile models don't necessarily mean happiness. For some kids, or even adults, the smile is actually an anger smile. But if you have no idea of the context, your recognizer of emotions can be extremely bad. In fact, emotion recognition as a problem is a very hard problem, because it turns out inside the brain, there are no labeled emotions. They're only labeled because you learn as a child that, if you fall down and you scrape your knee and you cry, your mom will say, I'm sorry you were sad. So now you have a label for that thing you're feeling, and you call it sadness. But if you're in another culture, that exact thing may not be labeled. And so, the brain is this very fluid machine that's learning all the time, and we're throwing labels through experience. There's nothing fundamental in the brain about sad, happy, right? This idea of basic emotions, it's been debunked in neuroscience. There's a wonderful book called How Emotions Are Made. And I really, recommend that everybody read it. I warn you, it's a little dense, but it's kind of the definitive thing. So the key points to answer your really good and really hard question is that there are no clear emotions in the brain, and therefore you can't really detect them. You can't look at someone and say, I know you're feeling such and such. What you're feeling is some soup, and I'm trying to project some meaning to that based on the context that we're in. So you need the context, and then you need to say, well, every time you do this thing with your face, and you say this thing, it is a sign of something related to sadness. So we're going to label it as sadness, right? So it's a very personal, individualized thing. And it's especially individualized in autism, where emotion expression is very atypical, right? So for example, a child might look out of the corner of their eye and they might not smile, but that's about as happy as they get. And so you have to learn a really personalized model. It's not one size fits all. It's not like I'm going to take, a giant data set of videos from Skype or Google and train emotion recognition on that, because that will work in some really narrow set, but it won't work in the real world. So all this is to say that it's a wonderful problem. It's a really interesting problem. You can solve it in some narrow domains. Like, remember the lying example I gave? Detecting lying turns out to be really easy. It's an easy problem, but it's not an easy problem to detect emotions of someone in the real world. And so the difficulties of problems are sometimes unpredictable. And that's why it's so interesting to start working on them. So jump in, I say, jump in and help out.
Thank you.
All right, so right now we're gonna take a question from the Q&A session. So I'll just pick the first one. So yes, Mansi asked, what is the difference between a humanoid robotics and a manipulation robotics?
Okay, so right, that's a good question about understanding the field of robotics. So usually robotics gets, people who do research in robotics end up doing something around navigation, right? So that's how the robot moves on the ground, right? So, or they work on manipulation, which is how the arm moves on the robot. So that's, neither one of those is human-robot interaction. Human-robot interaction can be about how the robot moves, right? Like social use of space, don't get too close to me. Or it could be how it waves at you, which is the use of the arm for social interaction, right? So these are completely different things that might have an intersection, right? So historically, people worked on navigation or they worked on manipulation. Now people are starting to bring the two together, mostly not, but they're starting to bring them together into something called mobile manipulation. So it's mobile and it manipulates. So humanoid robots are a tiny subfield of robotics because they're really, really hard to get. Like, there aren't lots of them. You can't go into a robot store and buy a humanoid. And if you could, it would cost a lot. So a humanoid is obviously all of those things. It's navigation and it's manipulation and it's balance and it's expression. It's really hard. And so that is a really small new field. And so it's a tiny subset of robotics. Most of robotics is about simpler robots that either navigate or they manipulate or they're doing some kind of social interaction like ours, right? So you could do human robot interaction with the robot, as you saw, that is just on the tabletop and it has some amount of motion, but it isn't really manipulating and it isn't really navigating. So it's really important to realize how big and broad robotics is, and it keeps growing. Now with soft robotics, people are starting to look at things that are inflatable and bendy, and that's a whole new area, right? So we're never bored. We never have a shortage of problems to work on.
I see, thank you. And also, I have a question in a room, and it asks, have moral implications ever stopped you from performing a certain research project because you're working so closely with humans?
Absolutely. So everything we do goes through human subjects approvals. In fact, as it happens, just over the pandemic, I was a VP at USC of research. And so the entire human subjects program reported to me, and I have a tremendous respect for what that program does. They check the ethics of every study and every bit of research that involves humans. So we don't do anything without it going through what's called Institutional Review Board, IRB, which tests for any form of potential abuse of human subjects, whether it's through paying them too little or paying them too much, or them getting hurt, or them getting like just thinking that the robot is the greatest thing. And like with kids with autism, what if the kids really liked the robot and they didn't want us to take it back after a month? We had a whole separate plan for that. We were actually ready, and in some cases did leave the robot longer so that the kid would be okay with us eventually taking it back, because we didn't want to make them overly sad. So there's so many issues related to ethics. You use the term moral, but it's really ethics is the broader field. Morality is under ethics. So ethics is this bigger field, and we have to care about ethics in our work in AI overall as a field. And so I encourage everyone to think about that. And absolutely everything we do in HRI goes through human subjects approvals. So that's a good question. It's good that you're thinking about that.
All right. So now we take one more question from the live web. So the question asks, will the field of robotics, especially houseboat robotics, get affected significantly with the developments in AGI? is deep reinforcement learning the go-to technique for researchers to get into the field from an AI ML point of view?
There is no go-to technique. So, I work a lot, I work with Google, I work with Amazon. They want people who know lots of different machine learning methods. Deep learning is useful for very narrow skills. So it could be very useful for very specific things. DeepRL is kind of it's the rebirth of reinforcement learning. It's not very generally useful. So people do use it, and it's a very useful skill to have. It's a very useful tool to have in your toolbox for machine learning. We do deep RL for certain kinds of things like policy learning in the real world, sure. But it's not it doesn't generalize very well at all, right? It takes a while. So it has a lot of flaws. So don't ever say, is there a go-to thing? Because this is a really hard field. And there's a lot, why do you think there are tens of thousands of researchers working in industry and in academia on these problems? Because they're really hard. So you can solve easy things easily, and then everything else is a wide open problem that people are still working away at. There is no go-to solution for anything in robotics. It's too hard. So in general, in AI, if you're looking at a hard problem, if it's a narrow problem, you might have a solution. But anything harder than that, generalizing across multiple tasks, learning over a long period of time, lifelong learning, understanding context, understanding common sense. Those are wide open problems that no one frankly knows how to solve. But that's good because we have a lot of more work to do and you all can help us. But I do want to say it's useful to learn tools, right? You should learn lots of tools, but I think you need to understand these are just tools. They're not solutions to big problems. There's a toolbox, and you try to fix the problem with the tools, and the tools are not perfect. And then you either build better tools or you adapt the tools, but don't get obsessed with the tools. Tools are not solutions. They're just tools.
All right, thank you. We have one more question coming from the room.
Hello, I had another question again. With the different robots you're building and the mixed reality, a lot of that equipment seems pretty expensive. How have you worked toward accessibility for kids or adults, whoever's using the robots?
Got it. I'm cutting your question short because I see there are a whole lot of other questions in the webinar that I want to get to. So that's a great question. In fact, the work that we're doing is extremely accessible. So right now, I mentioned that we're developing a soft robot. It's based on a colleague of ours at Cornell, Guy Hoffman, who developed a robot called Blossom. You all should look it up. It's a squash and stretch robot that you can build for $100. So we're developing some additional things for that robot so that people can have a really good research robot for well under $500. So that's cheap, right? It's understandable that it isn't something that, any kid can buy, but a $500 robot today means, a $20 robot 5 years from now, because at economies at scale. So actually our robots are designed by design to be low cost, because I very much appreciate exactly the point you're making, which is that, we're not trying to make robots only for the well-off people. But, there are other areas in robotics where it's so hard early on. And so the things that people develop in early prototypes are expensive, but that doesn't mean that they can't get cheaper with time. We, however, try to make them pretty cheap to start with. So we can do that. You can't do that in surgical robotics. It's just not, it's a different kind of robot. But in what we do, we can actually make them cheap. And so we do. I feel like we're going to run out of time if you don't go through some of these. Should I go very quickly through some of the webinar questions?
Thank you. Yeah, if you would like to look at the webinars, I can read them to you, or you can just read them off.
No. I'll do it. I'm gonna just randomly sample. Okay, last question. How can you get as an undergrad involved in this field? Great question. Actually, on my lab's website, we have answered that very question. We have information on my lab's website, Interaction Lab, that says, how would you get into this research? And it gives you a list of software tools, learning ROS. It tells you a bunch of stuff that you need to know. It's on my website. So you can look it up right there under contact. Under contact, there's a thing about how to get into this field. All right. So that question has come up so many times. I've answered it generically. Let's see. How can they be used in day-to-day life? Well, there are companies that have developed socially assistive robots on the market. So for example, there's LEQ, which is a robot for the elderly. Then there's Moxie. A full disclosure, that's a startup that I started. That's a robot for child development. There are a bunch of other examples out there on the market, and there's child development. It's not just education. There's elder care. So there are all kinds of domains. My lab historically has also worked on stroke rehab. So there, all kinds of domains. So it's by no means limited only to medical things. And I expect in the next decade that we'll see more and more of it, because the pandemic really exposed the need. But venture capitalists need to invest in this. They need to stop investing in apps. That's hard because apps are cheaper. Can design thinking be combined with generative design? That's a great question, and I hope so. And I really, really think that design thinking has kind of become a fad, and it has its own, set of mantras and structures. And I really think that people should push design thinking along with generative design and something called PAR, participatory action research, which is when you bring the people who are supposed to be the users into the process. Because you should never, ever be designing something for people if you're not representing that group, because you really don't have a clue. Let's face it. When I'm designing for stroke, I don't have a clue. I haven't had a stroke, thank goodness. And I don't personally have autism. So I have to bring in the very users into the process. And so that's what needs to happen. And it needs to happen much more. Unfortunately, there are too many companies that are not really paying attention. They've designed something and they think if they push it on the market, people will buy it. Like if you build it, they will come. Well, not so much. At least they won't stay. Let's see what else. For some reason, many questions have disappeared. I guess maybe I've answered them. When developing that aim to change the behavior, have you looked at the guarantees that the robot will always behave in accordance with human values of preventing adversarial cases? Yeah, so this fits under ethics, right? So when you're developing robots that are trying to change behavior, indeed, in our case, we're in the therapeutic space, right? So we're saying if you're choosing to, you're always choosing to interact with the robot, right? And you're choosing, and you know that what it's trying to do is, let's say, help you self-regulate if you have anxiety. And that is something that you've agreed ahead of time is the thing that the robot is working on and you're working on it with. So that's fine. Now, if your robot is going to have some secret goals that it's trying to achieve that you don't know about, that's a very shady ethical realm. And that is something that people worry about legitimately, right? Because it's kind of like your smart speaker, you ask it, for example, what's the weather? And it tells you, and then it offers to sell you something. Okay, so that's shady, right? Because, it's basically, it has its own goals that it's trying to achieve. And I don't think these goals are, like people always worry about like, oh my God, is it going to be an evil goal? No, it's just going to be a consumerist monetized thing. It'll be selling you stuff. And that's not great, right? So you're right. We do have to worry about the ethics. We stay in the realm of like, this thing will teach you X. This thing will help you with Y. And so you sign on as a user by saying, I want to learn X. I want to get better at Y. But you are right to worry about this. These are all ethical issues that we really need to think about when we design these systems. So right on, keep asking and keep probing, because it's very easy, especially if there is a financial incentive. It's very easy to kind of cut corners. Can emotions and thoughts in general exist on a manifold? What manifold? There's no manifold. You have to know like what manifold of what. So is that manifold continuous? Largely manifolds are. So congratulations on an extreme number of buzzwords in your question. But whenever you ask a question, I absolutely recommend that it actually be meaningful. When you ask questions, don't try to show off. Instead, ask a question that is answerable. So that is not an answerable question. I'm sorry. I don't mean to be harsh, but life lesson. Always ask a question that is meaningful. Emotions are absolutely a highly dimensional, not understood space in the brain, right? Because we don't even know what does it mean to have emotions in the brain. It's a combination of electrical signaling, it's a combination of hormonal signaling, and it's a combination of activation passing through various regions of the brain, right? So nobody can even model this today. There's some imaging that does modeling, but imaging is just blood flow. So that's just one kind of crude measure of emotions. And then you have expressions in the body and face, and then you have context. So is it a manifold? Sure. Is it continuous? Sure. Can we describe it and understand it? Not at all. And so what's happening in emotions is we're taking slices, right? We're saying, I see your face, I see your body movement, I can maybe look at the history of that. I hear what you're saying. And maybe I know something about the context, although the context is usually poorly described. So we put all that together, we do some kind of machine learning. It's very crude, but it gives you something. The part that is most important is behavior, not what you feel inside, because no one has any control over it. Like no one knows what's inside your head. What matters is your behavior. So if I see some combination of signals, and that always leads in you getting really angry and not being able to control your anger some seconds or minutes later, that is useful to know because it is the behavior that we want to alter. So if I'm trying to help you manage your emotions, it's useful for me to know how you behave leading to that thing that I want to not happen, so that I can, when I see it kind of starting, I can, do things like say, oh, this is a good time to step away. How about 5 jumping jacks? Well, let's take 10 deep breaths, right? So it's not that I have any access about what's going on inside your head. Can't have that. And even if I did, I wouldn't know what to do with it. So forget the manifold. What matters is that I can predict the behavior downstream and try to interfere with that. That's a very fundamental thing about human behavior. It's not new. What's hard is that it's different for everyone and you have these strong temptations. And once you are on a spiral, you can't change. So how do we get in the middle of that? So I say that not to make you feel anybody bad, but I just want you to understand that everything about human behavior is complex and interesting, and it doesn't lend itself to math, even really complex math. We don't understand it. You can only put math around things that you understand pretty well. And we don't understand human behavior well at all. But if you want to understand human behavior better, I would recommend that you read papers in behavior economics. That is a beautiful field. And they run these beautiful studies and they show things like our cognitive biases, like Danny Kahneman, who got the Nobel Prize in behavioral economics, who studies things like things that we tend to do, even though they're irrational, but we keep doing them. Well, that's useful to know, because if I know something that people tend to do, that gives me a prediction, a bias that I can now use to help change behavior. So there's an entire Wikipedia page on human biases in terms of cognitive biases. So check that out. That I think is a lot more useful than trying to put a whole lot of math around something that we don't frankly understand. And also the book on how emotions are made. Now that's a deep book if you'd like to read something pretty darn dense. We have a lot of resources, by the way, on my website. So if you go to my Interaction Lab page, under contact, we have a bunch of resources. I also have a mentoring page under my personal page. So, my own page, Google me. There's a mentoring page there. I have a bunch of resources, a lot of interviews where people ask me the kinds of questions you might be thinking about asking. They're in there. So, I hope some of this is useful to you folks, because you're going to go and do amazing things. And I look forward to that.
All right, thank you, Dr. Matarić. So we're running out of time. So I have 2 questions in my hand from the room. I guess we'll just finish these 2. I think you've already answered a little bit of the first question. So the first question asks, what kind of side effects can this type of learning with social assistive robotics might have on, say, babies or children when they're interacting with when they interact with real people in a long future?
Well, I think with any technology, and in fact, any therapeutic context, you have to make sure that there is a variety of experiences, right? So you would never leave a child with a robot for 24 hours for 7 days a week, because obviously that would have some serious developmental influences, right? You would also like to not leave a child in front of a screen for many hours a day. And yet that's exactly what happens to all children now, because guess what? That's not good developmental experience either. Just, using your finger to go left and right on a screen. And that's what's happening. You would also like to not leave a child with a neglectful parent with an addiction. And that happens a lot too, right? So the point is, development is about the full collection of experiences that a child goes through. And it's really important that those experiences present a lot of opportunities to learn, and also a lot of experiences of support, safety, and love. So the robot's role is not to provide love. There should be someone else there providing love. But we would like the robot to provide the things that the child doesn't otherwise get, right? So if they're not exercising their arm and it's not working, that's where we want the robot to help. If they are not able to manage their emotions and they need practice with that, and there's no one to practice with because other kids won't play with them, well, then the robot can fill that gap. The point is that the robot is filling a gap. It's not trying to serve as a parent. This is kind of like the idea back in the day, you all can't relate to this, but before streaming, there was TV and people would leave their kids in front of the TV. Well, TV is not a babysitter, right? So again, you have to be very careful about how you use these technologies. But if you don't develop them, what's the alternative, right? So the alternative is, do we not develop them? Oh, and then what's the alternative? The alternative is the kid gets no play. They get no support. Okay, so you have to really look at all of the picture and then figure out what is the point of the thing you're developing? What are the risks? How do you mitigate the risks? But again, really good of you to be thinking about that. Really good.
All right, thank you. And the last question is, what do you think that will be fundamental in order to bring the social assistive robotics within marginalized sections or adapt to different cultures in a way that it is accepted?
Thank you so much. That's a great question. It's a good closing question because I actually have at least one PhD student who's very concerned about this. And it's a really difficult thing to study. Because, for example, if you want to make the robot culturally acceptable, you can't pick any particular culture to model because that becomes profiling, right? Like we were talking about, how can we make a robot that's really relatable to inner city kids in Los Angeles? Well, the inner city kids in Los Angeles are a particular cross-section of cultures. If we model them, it starts to look like really like we're profiling, right? And so it's very tricky. But I think, in the long run, of course, the answer is, these systems need to be designed by people who are members of the communities that are going to use them. That is the answer to all things. You cannot have one group of people who are designing and another group of people who are using. Nope, that does not work, and it is proven not to work. Just like you shouldn't have one group of people teaching and the other group of people, learning. We need to have diversity everywhere, right? So that's a key thing. So you can get diversity through training data, but that's not enough. If the people developing the system do not represent the user community, then there's always going to be bias. And so we are, I take huge efforts to have a very diverse group of students, not only because it's the right thing, but because they're just so much better at coming up with ideas and problems and solutions than I could. I mean, we all have our very limited view. So I think the fundamental answer to your question, which is a deep question, is that we need to have participation and inclusion broadly in the process of developing the technologies, which is why all of you listening to this need to, one, work on important things, and two, you need to help and recruit. You need to pay it forward. You need to be mentors for younger students. I've done a lot of mentoring for K-12. Why? Because that's the future, right? And now I'm old. So I have my students, my undergraduates mentor K-12 because they're more relatable. I look like a mom now. Oh my goodness, that's not very exciting. But my students are exciting. When Lauren comes in and she talks about the work with babies, that's really inspiring because she's just a few years older than you folks. And look what she's achieved. And she thinks very deeply about what this is going to do to the world and where should she go on next when she finishes her PhD to do meaningful work. So that's the kind of role model that we want. And having all different role models from the lab and from every lab, I think that's what's going to get us there. That's the only way.
All right, thank you, Dr. Matarić, and thank you for the insightful talk. I think that effectively concludes our Q&A session.
Thank you for having me.
For sharing all the information. We really appreciate it.
My pleasure. Thank you, folks.